So based on the last video magic explanation that I provided, I was fearing that I might get this question. Am I always going to be disappointed by the magic? When I give you a black box mechanism where you just need to know the outcome, you don't necessarily need to know how it works, is that always going to be disappointing? And my answer is, maybe. Depends on how you feel about this one. I'm going to explain how the boron R group bonds, the boron carbon bonds, become hydrolyzed by the peroxide. And really the only reason why I'm going to do this is because it keeps illustrating the key points. A nucleophile is going to add to this thing, which is always electrophilic, and then strange things happen. So again, this is really an illustration of the fact that boron always has an empty orbital on it, which drives its reactivity no matter when you encounter it. If you see aluminum, if you see boron, you know that they have empty orbitals until they have four things bound. But as soon as they have four things bound, then something bad happens almost immediately. So this mechanism, you don't need to know the details of it. The reason why I'm showing it to you is because it really illustrates how this compound works. So you always have an empty orbital, which means that you're always going to be looking to put nucleophilic stuff into that empty orbital. You're always going to be donating electron density into it. So the borane is here. That is the end result of the previous step. And what happens is the peroxide comes and makes a bond to the boron. And this will not necessarily be an equilibrium step. I'm not going to worry a ton about the mechanistic details here for reasons that you will see shortly. Like for instance, I'm going to go ahead and skip the deprotonation step that must be happening. Again, this is more pseudo-mechanistic work. I'm not interested in showing you all the details. I am interested in showing you the big picture idea. So because we're doing this in base, maybe this added first and then become deprotonated, or more likely you just the boron now has a full-on minus on it, and that's weird and that's bad. But we also have a group nearby with an exceptionally weak bond. And this is something that will come back later in the course, which is again another reason why I wanted to point it out. Hydrogen peroxide, or peroxides in general, have an extraordinarily weak oxygen-oxygen bond. This really wants to break, and in particular, it wants to break to form hydroxide. This is ordinarily a terrible leaving group, but we're fragmenting a really crappy bond, and we're running this reaction in hydroxide anyway, so it's clearly not a problem to have hydroxide floating around. So, where are the electrons that could cause this to happen? Well, they're in this boron R group bond. They just slide over, and that pops right off. So the upshot of that is that now we have, of course, a boron bound to a single oxygen with an R group on it, and the boron again has two other R groups on it, and there we sit until, of course, another peroxide happens to come along, and the peroxide will add to the boron, which then brings us back here, only now rather than having three R groups, we have two R groups and an OR group, and the process happens again. Again, I'm not particularly interested in following through the mechanism all the way, but basically you eventually convert this, and the reason why it happens is because hydrogen peroxide, or peroxides in general, have an exceptionally weak oxygen-oxygen bond, and you can break that easily enough as long as there are sources of electrons nearby. And once you have added a peroxide to the boron, that creates a source of electrons. The boron was formally happy because it only had an empty orbital, but as soon as you bind something to it, then it is formally unhappy. It has too much electron density. So those electrons flow over, break that oxygen-oxygen bond. Eventually, of course, this converts the boron into this material, and then the way that things happen is once you get down here, then a hydroxide can add, and one of those will leave as O-, and since what we care about is the RO-, that's what we end up isolating out of the far side. The final thing that you can isolate, if you wanted to, is BOH3. That's the inorganic stuff that you make, or possibly with another hydroxide bond to it. Again, that'll pop on and off, and it doesn't really matter. The thing that we care about isolating is, of course, the RO-, which means that at some point in there, you have to add acid to quench, because what you actually isolate is the alcohol. That's the thing that you care about. Again, the magic here is peroxide has a super weak bond. Boron really wants more electron density, but as soon as it gets it, it really doesn't want to have extra electron density, which is why boron is so reactive.